We're going to dive deep into the world of port forwarding, both static and dynamic, and understand the intricacies of virtual private networks, that's VPNs, and explore the functionality and implementation of SOCKS proxies. These are fundamental components in the toolkit of network administrators, cybersecurity professionals, and even everyday users seeking to maintain privacy and unrestricted access in a networked world. Our journey will uncover the practical applications of these techniques, the theory behind their operation, and the ethical considerations that come with their use. By the end of this lecture, you'll have a solid foundation in leveraging these advanced tunneling techniques to your advantage, whether it's for overcoming egress filtering in a corporate setting, bypassing geo restrictions, or securing your network traffic from prying eyes or intruders. Let's start by understanding what tunneling really is, especially within the realm of network security. At its core, tunneling is a method by which we encapsulate one form of network traffic within another. Think of it as sending a letter within a sealed envelope through a courier service. The courier doesn't need to know what's written in the letter. They just need to deliver the envelope to its destination. Similarly, in tunneling, our data packets are the letters securely wrapped within another layer of communication protocol, ensuring they navigate through the network undetected and undisturbed by intermediary nodes like firewalls. Why is this really important? Well, in the context of network security and administration, firewall serves as a gatekeeper. They scrutinize incoming and outgoing traffic based on predetermined security rules, blocking or allowing data packets based on these criteria. While firewalls are crucial for protecting networks from malicious actors and unwanted traffic, they can sometimes be overly restrictive. This restrictiveness can hinder legitimate network access for users, block access to certain services, or even impede remote work and collaboration. It's in these scenarios that tunneling techniques become invaluable. By effectively disguising the nature or destination of our data packets, tunneling techniques allow us to bypass firewall restrictions, whether it's to access a blocked website, ensure secure communication across an insecure network, or maintain privacy and anonymity online. Tunneling provides a pathway through the digital barriers erected by firewalls. Throughout this lecture, we're going to delve deep into the specifics of various tunneling techniques, including static and dynamic port forwarding, the operation of VPNs, and the role of SOCKS proxies. Each of these techniques offers unique advantages and use cases in circumventing firewall restrictions, enhancing network accessibility, and securing data transmission across the internet. Understanding these techniques not only empowers you to navigate through restrictive network environments, but also equips you with the knowledge to implement robust security measures for your own networks. Static port forwarding is a fundamental concept in networking that involves redirecting network traffic from one port on a network device to another port on the same or a different device. Essentially, it's about mapping a specific port from the external side of a router or firewall to an internal IP address and port within a private local area network or LAN. How does this work, you may ask? Imagine you have a web server running on a computer within your LAN, which is behind a router. The server is set up to listen for incoming connections on port 80, the standard port for HTTP traffic. That's port 80. However, From the outside world, this server is unreachable directly because of the router acting as a barrier. By setting up static port forwarding on the router, you can tell it to forward any traffic that comes on a specific external port, say port 8080, directly to port 80 on your web server's internal IP address. This way, anyone trying to access your server from outside your LAN can reach it by using your router's external IP address and the forwarded port number. Use cases for static port forwarding are vast and varied, often found in network administration and security contexts. Here are a few scenarios where it's particularly useful. First, we're going to talk about hosting servers. If you're hosting a web, game, or any other kind of server, static port forwarding is essential for making your server accessible for the internet from the internet. Remote access for accessing internal network resources from the outside, such as home surveillance systems or personal file servers. Static port forwarding can provide a direct pathway. Security and monitoring. In a security setup, port forwarding can be used to direct traffic to network monitoring tools or intrusion detection systems or ideas without changing the network infrastructure. While static port forwarding offers a straightforward solution to bypass certain types of network restrictions and make internal services accessible from the outside, it's also crucial to be mindful of the security implications. Opening ports on your router can potentially expose your internal networks to vulnerabilities or attacks if not properly secured. Therefore, it's imperative to implement strong security measures like firewalls and encryption to protect the forwarded traffic and the internal services behind and the internal services being exposed. A technique that builds on the concept of static forwarding that um, a technique that builds on the concept of static forwarding but introduces flexibility and enhanced security for managing network traffic. Unlike static port forwarding, which directs traffic from a specific external port to a fixed internal port and IP address, dynamic port forwarding allows for the automatic redirection of traffic to multiple destinations based on the requesting client's needs. This is achieved by creating a secure tunnel, often through an SSH or a secure shell connection, that serves as a gateway for all requests from the client. How does dynamic port forwarding stand apart? It functions by setting up a local proxy server on the client's machine. When the client makes a request, say to visit a website, the request is sent through the SSH tunnel to an SSH server. The server then forwards the request to the destination website. The response from the website travels back through the tunnel to the client, effectively bypassing any direct interaction with the network's firewalls or egress filtering systems. This mechanism not only secures the data in transit using the encryption provided by SSH, but also obscures the destination and origin of the data packets, enhancing privacy and circumventing monitoring or restrictions placed by network administrators. Dynamic port forwarding is particularly useful in scenarios where secure, flexible internet browsing is required. Let's delve deep into the specific use cases. Secure browsing in public Wi-Fi networks. When using untrusted public Wi-Fi networks, dynamic port forwarding can secure all your browsing activity, protecting it from potential eavesdroppers or malicious actors on the network. Circumventing geo restrictions and censorship by routing your internet request through an SSH server located in a different geographical location. You can access content and services that may be restricted in your current locale or your current location. Secure access to corporate resources. For remote workers, dynamic port forwarding can provide a secure path to access internal corporate resources without exposing them directly to the public internet. The flexibility and security benefits of dynamic port forwarding make it a powerful tool for individuals and organizations alike seeking to enhance their internet browsing security and privacy. However, it's important to note that setting up dynamic port forwarding requires access to an SSH server, and the configuration can be slightly more complex than static port forwarding. Despite these considerations, the added layer of security and the ability to dynamically route traffic based on the client's requests offer compelling advantages for a wide range of networking challenges. SOX proxies, an essential tool for network security and anonymity. SOX, which stands for Socket Secure, is a protocol that facilitates the routing of network packets between client server applications through a proxy server. It's designed to provide an intermediary for traffic routing, making it a valuable asset for bypassing firewall restrictions and ensuring privacy. The SOX protocol has evolved over time with two main versions widely used today. There's the SOX 4 and the SOX 5. Let's break down these two and talk about their key differences. SOX 4. SOX 4 is primarily SOX 4 primarily deals with TCP connections, making it suitable for applications where data needs to be transmitted reliably. It doesn't natively support UDP or authentication, which limits its use in scenarios requiring higher security or support for UDP-based applications. It supports it operates at a lower level, making requests based on IP addresses rather than domain names. This means that the client needs to resolve the domain name to an IP address before making a request through a SOX 4 proxy. SOX 5. The SOX 5 is more advanced and a secure version. It supports both TCP and UDP connections, expanding its utility to a wider range of applications, including those that require faster connectionless data transmission. One of the significant enhancements in SOX 5 is its support for authentication methods, providing a mechanism to secure the connection between the client and the proxy server. This adds an additional layer of security, ensuring that only authorized users can access the proxy servers. SOX 5 also supports domain name resolution through the proxy, which means the proxy server can directly resolve domain names. This feature enhances privacy by hiding DNS queries from local ISPs and potentially circumventing DNS-based filtering and logging. Comparing both SOX 4 and SOX 5, the key difference between both boils down to the SOX 5's support for both TCP and UDP protocols, authentication mechanisms, and the ability to handle domain name resolutions. These improvements make SOX 5 a more versatile and secure choice for navigating through network restrictions and ensuring privacy. SOX 5 proxies, especially SOX 5. The SOX proxies, especially SOX 5, are widely used for various purposes, from secure browsing and accessing geo-restricted content to peer-to-peer sharing and bypassing internet censorship. Their ability to operate at a lower level than HTTP proxies, handling any program or protocol without understanding or modifying the traffic, makes them a powerful tool in the network security toolkit. Python's socket library is a low-level networking interface which allows us to create both client and server programs. The socket library can handle different types of protocols, including TCP, which is primarily used in conjunction or together with SOCKS proxies. But using this library, we can directly manage the establishment of connections, sending and receiving data, and closing connections. Going deeper into a basic example of how to create a simple SOCKS5 client using Python programming language. This client will establish connection to a SOCKS5 proxy server and then use it to make a request to a target server. The sample code above demonstrates establishing a SOCKS5 proxy connection to example.com through a proxy server. The script begins by connecting to the proxy server and performing a three-way handshake to negotiate a no authentication connection. It then requests to connect to the target address through the proxy. If successful, the connection to the target through the SOCKS5 proxy is established, allowing data to be sent and received through this tunnel. Remember, this is a simplified example which is intended for just illustration. It's intended to illustrate the process of using a SOCKS5 proxy within Python. Real-world applications might require handling various scenarios, including the different types of authentication, error handling, and asynchronous communications. It's important to understand that these firewalls are designed to control incoming traffic, to protect internal networks from unauthorized access and potential threats. However, there are legitimate scenarios where bypassing these restrictions is necessary for operational efficiency and connectivity. Techniques and tools. Port forwarding. Utilizing port forwarding to redirect incoming connections to the desired internal service can effectively bypass ingress restrictions. Virtual Private Network Services or VPN services. Establishing a VPN connection allows for secure encrypted tunnels that can bypass firewall restrictions on incoming traffic, enabling remote access to internal resources. Web proxy servers. Acting as an intermediary for requests from clients seeking resources from other servers, web proxies can help in circumventing firewall imposed limitations on incoming web traffic. Legal and ethical considerations. While discussing strategies to bypass ingress firewalls, it's paramount to emphasize the importance of legal and ethical considerations. These techniques should only be employed in scenarios where they are legally permissible and ethically justified. Unauthorized access to or manipulation of networked systems can have serious legal and professional effects. Always ensure that your actions are in compliance with the relevant laws, relevant policies, and the ethical standards. Egress filtering, on the other hand, is implemented by organizations to control outbound traffic from their networks. This practice is crucial for preventing data exfiltration, ensuring data loss prevention, and blocking access to malicious online destinations. Challenges. restrictive access. Overly restrictive egress filtering can impede access to legitimate resources, affecting productivity and operational efficiency. Complex management. Maintaining an egress filtering policy that balances security with accessibility can be challenging, requiring continuous updates and configurations. Methods to bypass egress firewalls, tunneling techniques. Utilizing VPNs or SSH tunnels can encapsulate outbound traffic in a manner that evades egress filtering, allowing for the secure transmission of data. Proxy usage. Employing external proxy servers can help redirect web traffic through different ports or protocols, effectively bypassing restrictions on outbound traffic. In the context of bypassing firewalls, both SOCKS 5 proxies and virtual private networks serve as powerful tools, each with its unique advantages and considerations. The SOCKS 5 proxy use cases. Ideal for specific applications that require change in IP address or to circumvent geo restrictions. It's particularly useful for scenarios requiring minimal overhead and maximum speed, like streaming or peer to peer sharing. Performance generally offers faster speeds due to a lower level of encryption and lack of data routing through a third party server. And security features provides anonymity and privacy to some extent, but lacks end-to-end encryption, making it less secure than the virtual private networks. Okay, VPNs use cases suited for users seeking comprehensive online privacy and security, remote access to restricted networks, or extensive internet browsing protection. Performance might be slightly slower than SOCKS 5 proxies due to encryption, overhead, and the process of routing traffic through a VPN server. Security features. It offers robust encryption, securing data transmission against interception or eavesdropping, and providing a high level of privacy and security. The situational advantages of both SOCKS 5 proxy and the VPN. The SOCKS 5 proxy is the SOCKS 5 proxy is advantageous for quick, specific tasks requiring anonymity without the need for comprehensive encryption. And on the other hand, VPN is preferable when securing all internet activity, ensuring data privacy and accessing restricted networks is paramount.